Yes, I thought it would be nice to talk about this Moore-Tachikawa conjecture in this specific seminar because, well, that's a seminar about geometry, physics, and representation theory. And this Moore-Tachikawa conjecture is something which is right at the intersection of the three. Although I won't say too much about the physics point of view, which is the origin of this conjecture, I think it's a very interesting conjecture. So let me begin by a brief overview of the talk. These two physicists, Moore and Tachikawa, made this conjecture in 2011, which is that for each complex reductive group, there is some kind of two-dimensional topological quantum field theory, where the target category is some different category of holomorphic symplectic varieties. So I will say in detail what is this conjecture later in the talk, but for now, let's just say that a solution means constructing a certain holomorphic symplectic variety, WG, associated with this complex reductive group G. And so they had a physical argument for why such a TQFT should exist, and it's taking the Higgs branch of some supersymmetric quantum field theory, but they couldn't construct it rigorously for all groups, and so they asked the mathematical community to work on that problem. In fact, they say in the abstract, mathematicians are huge to construct eta G rigorously. And a few years later, it was solved by Ginzburg and Kazhdan in a very interesting way. Their solution is to construct WG by some kind of symplectic reduction by a group scheme. And so that's the interesting bit here, that it's not symplectic reduction by a group, but by a group scheme. But their construction is ad hoc, and it's apparently not clear if there's such a general theory of groupoid by or reduction by a group scheme, of which this is a special case. Their construction uses some special properties of this particular group scheme, such as the fact that it's abelian, for instance. And so this led me to ask the question, is there a general theory of symplectic reduction, which includes standard symplectic reduction and also the Ginzburg and Kazhdan examples? And the point of this talk is to review this Moore-Tachikawa conjecture and the solution by Ginzburg and Kazhdan, and then explain that yes, there's such a general theory of symplectic reduction which recovers the Ginzburg and Kazhdan example in a very nice way. So the answer to the question is yes, there's a notion of symplectic reduction by a groupoid along a submanifold, and that's the right setup to generalize. Group schemes are not general enough to get a consistent theory. You have to go to groupoids, and the important bit here is the fact that we're doing that along the submanifold. That's the new piece of information. Because even if we start with a group, the fact that we're taking this reduction along a submanifold gives us new things. So for instance, the usual symplectic reduction is recovered as a special case at n-level C in the dual of the Lie algebra. And this is generalized to symplectic reduction at a submanifold S. So you replace the C here by a submanifold of the dual of the Lie algebra. And the difference here is that the thing which stabilizes Xi is now generalized to something which is no longer a group, but a subgroupoid of the cotangent groupoid associated with G. So we'll review this notion of groupoids and symplectic groupoid. The important bit here is that it's not necessarily a group. No, it's a groupoid. And this helps us clarify the Ginzburg and Kazhdan construction, because now it can be viewed simply as a reduction of the cotangent bundle of G cubed by G cubed, where G cubed acts by right translations along a certain submanifold, which is the diagonal embedding of a Slodový slice. So we'll explain that later in the talk. And also as a bonus, we recover other special cases of symplectic reductions. For instance, we recover the slice construction. If you take the pre-image of a Slodový slice under a moment map, this is the symplectic submanifold in general. And this is a special case of this, where this groupoid is trivial when you have a Slodový slice, so we recover that fact. Another thing is, if you know about that, there's the notion of Mikami-Weinstein symplectic reduction by a groupoid, which is a special case of this construction where S is a point here. And finally, so recently me and Peter have started thinking about singular versions of this when we work with complex analytic spaces or complex algebraic varieties and stratified symplectic spaces. So I will briefly mention that at the end of the talk. Okay, so let me now review this notion of Moore-Tachikawa TQFT, unless there's a question before I continue. No? Okay, so recall that the TQFT, two-dimensional topological quantum field theory, is just a functor from the category of two coordisms to vector spaces satisfying the so-called Atiyah-Segal axioms. So in concrete terms, this category, but 2 is just a category whose objects are circles, or disjoint union of circles, or more precisely, one-dimensional compact oriented manifolds. And an arrow in this category is a surface with boundaries. And so this is an example of an arrow from 2 copies of the circle to 1 copy of the circle. And composition is the obvious thing where you glue these surfaces together. And the TQFT is just a functor from this category to the category of vector spaces. So you have to see where the circle, which is an object in this category, goes. It goes to a vector space. And the axioms are such that if you take 2 circles, this is mapped to the tensor product of this vector space. And so now a surface with boundaries should be mapped to a linear map from the corresponding vector spaces. And this should be made in a functorial way, such that gluing surfaces corresponds to composition of linear maps. So that's what a TQFT is. And Moore-Tachikawa TQFT is just a slight generalization of that, where you replace the category of vector spaces by another category, which they called HS. That's a category of holomorphic symplectic varieties. But this category is a bit strange. The objects are not the holomorphic symplectic varieties. The objects are complex reductive groups. And that's the morphisms or the arrows, which are holomorphic symplectic varieties. So an arrow from G to H, complex reductive groups, is not a map from G to H, but a holomorphic symplectic variety with 2 commuting actions of G and H, which are Hamiltonians. So they have moment maps. And the important bit here is to specify what is composition. If you have an arrow from G to H and an arrow from H to K, so that means that M and N both have an action of H. And so you can consider a diagonal action of H on the Cartesian product. And you just take the symplectic reduction along this common action. And that's the definition of the composition. It makes sense because G acts on M, and there's a residual action of G now on the quotient, and also an action of K. So you can view that as an arrow from G to K because there's an action of G times K on this symplectic reduction descending from the actions on M and N. So that's composition. Now to specify a category, you have to specify what is the identity of an object in this category. So an identity for a complex reductive group G is an arrow from G to G, which in this definition just means a manifold with 2 commuting actions of G and G. So, or in other words, an action of the cross product, which is Hamiltonian. And the obvious candidate would be to take the cotangent bundle, where this action is just left and right translations. So the lift of the action by left and right multiplications to this cotangent bundle. Why is that an identity? Well, it's an easy lemma that if you have any Hamiltonian G manifold M, you take the cross product with the cotangent bundle, and then you take the Hamiltonian reduction by the action on M and the right action on T star G. And this is isomorphic to your original manifold M, preserving the symplectic structure and also the moment map in the Hamiltonian action. So in these terms, we have that T star G composed with M is M. So T star G can be viewed genuinely as an identity in this category. Okay, so that's a genuine category, a category of holomorphic symplectic manifolds. And the conjecture by Moore and Tachikawa is that for each complex reductive group G, there is a topological quantum field theory we target this category. So, and there's some properties that this quantum field theory has to satisfy. First of all, the object, the circle, which is the generating object in this cobordism category, you have to send it to something. You say map it to the choice of complex reductive group G. And also the conjecture specifies what is the morphism from the empty set to the circle. So it's just the sphere with one boundary component. So we can think of that as a morphism from the empty set to the circle. And this functor has to map the empty set to the trivial group, and the circle we said is mapped to the complex reductive group G. And so this morphism here in the bordism category should be mapped to an arrow in HS. Oops, sorry. And an arrow in HS is just a holomorphic symplectic manifold with an action of G. And they specify that this manifold should be simply G times S, where S is a principal Slodovy slice. Recall that the Slodovy slice is a manifold of the, an affine subspace of the form F plus GE, where E, F, and H are an SL2 triple in G. And so that's a Slodovy slice. And principal here just means that these are taken to be regular elements. And well, this is inside G, but using an invariant linear form, you can identify this with the dual of the Lie algebra. And so you can view G times S inside the cotangent bundle once you trivialize the cotangent bundle by left translations. And this happens to be a symplectic submanifold of this cotangent bundle. So it has a holomorphic symplectic form. And the action by left translation is Hamiltonian with a moment map. So that's a genuine arrow from 1 to G in this category HS. And so that's the conjecture. And to solve this, it suffices to construct WG because that's, well, first I didn't specify exactly what I mean here by this pair of bands. Whether you view this as a morphism from the empty set to 3 boundary components, or you can view this as a morphism from one circle to 2 disjoint copies of the circle. The axioms are such that it doesn't matter. All these varieties will be isomorphic, so you just have to specify one of them. In the end, it will just be a holomorphic symplectic variety with 3 commuting actions of G Hamiltonian, or in other words, a Hamiltonian action of G cubed. Or if you want to say more precisely what it means to be invariant under all these difference representations, it means that there's an action also of the symmetric group of 3 letters, which permutes all these actions. And so there's a Hamiltonian symplectic action of this solidarity product. But in any case, yes?
Before you go on, how important is it in your definition of the holomorphic symplectic category that the manifolds actually are holomorphic symplectic as opposed to symplectic?
Oh, well, you could.
If we were not necessarily interested in this Moore-Tachikawa conjecture, say. Well,
the Moore-Tachikawa conjecture is about these homomorphic symplectic varieties, but maybe it's an interesting question if you can formulate a similar theory in the smooth category. I haven't really thought about that or seen anything about that, but that's something interesting we should think about, an appropriate analog in the symplectic category, but I haven't seen that before. In the end, what we want is that these are Higgs branches for some supersymmetric quantum field theory. So in the end, we want them to be actually Haber-Keller manifolds, although the Haber-Keller structure has not been constructed rigorously yet. So that's an open problem. Okay, so why is it sufficient to construct just this? Because in general, any surface can be chopped into pieces which look like the pair of bands or cylinders. And so by the gluing axioms, you can build every surface by just this structure. But also, of course, it has to satisfy some compatibility assumptions. for instance, the fact that if you cap the pair of band with, you cap one of the boundary components, you end up with the cylinder, means that this double G, if you take the Hamiltonian reduction with this G times S, which is the thing associated with the cap, it should be the cotangent bundle, because this is associated with WG, this is associated with G times S, and this is the identity in the Bordesian category of the circle. And so this is mapped to the identity in HS, which is T star G, and gluing corresponds to Hamiltonian reduction. So that's one of the things that this WG has to satisfy. And so now let's see a few of the examples just to give you a taste of the non-triviality of this conjecture. So those examples were new already at the time of the paper by Moore and Tachikawa when they made that conjecture. First, the case of SL2C. This WG happens to be just, well, it's a simple thing. It's just three copies of C2 tensored with themselves. And so this has to be a morphism from 1 to SL2 cubed because of the 3 boundary components. And so it has to have an action of SL2 cubed. And it's, in this case, it's simple to see. It's just a standard representation of SL2 on all these factors. But already there, we get some interesting varieties when you look at the full TQFT. For instance, if you look at the 4 boundary components on a sphere, you get the minimal nilpotent orbit in SO8, which is kind of strange. And well, this is a morphism from 1 to SL24, so it has to have an action of SL24. And where does this action come from? You can see it directly from the extended Dynkin diagram of that. So that's D4. So the extended Dynkin diagram looks like this. And it's a fact that if you delete a node in any node in an extended Dynkin diagram, the result will give us a maximal subalgebra of your algebra. And so if you delete the center node here, you have 4A1 sitting inside D4. And so you can see SL24 as a subgroup of SO8. And so you act on the minimal nilpotent orbit by conjugation. And when you go to SL3, it's even crazier. So the space associated with WG now happens to be the minimal nilpotent orbit in E6. It's a bit strange that we get the exceptional Lie algebra E6 coming from SL3. So let's pause a little bit to see how strange that is. So it's a TQFT. It's just a machine which associates with surface with boundaries some holomorphic symplectic variety. And we said that the cap has to be associated with G times S. And the cylinder, which is the identity, should be mapped to the cotangent bundle. You can also work out what is the sphere. So the sphere is just 2 caps glued together. And so it's a symplectic reduction of G times S times G times S. And it happens to be the so-called universal centralizer of this group G, which is another very nice variety associated with G. But then when you go to 3 boundary components or higher, you get these very wild varieties, which seems to be kind of completely out of the blue. So why E6 coming with SL3? And it's also nice to see where the action is coming here. So this is supposed to have an action of 3 copies of SL3, okay, SL3 cubed. And also you can see it from the extended Dynkin diagram. So the Dynkin diagram of E6 is this. And if you delete the center node, you get 3 A2 subalgebras. So A2 cubed is contained in E6 as a maximal regular subalgebra. And so this is contained in E6 and hence it acts on the minimal nilpotent orbit of E6 by conjugation. Another very nice Special case is when you look at the torus with one boundary component. Braverman, Finkelberg, and Nakajima showed that this is the closure of the subregular nilpotent orbit in G2. And also we can see the action. So this is one boundary component. It's a morphism of 1 to SL3. So it has one action of SL3. And again, you can see it from the Dinkin diagram, but it's more fun to look directly at the root system since this is rank 2. So the root system of G2 looks like this. And if you look at all the roots on the outer boundary, this forms a closed root subsystem because the sum of any two roots is either not a root or in this subsystem. And this is exactly the root subsystem. It's exactly the root system of A2. So there's an A2 sitting in G2 as a maximal subalgebra. And so SL3 is contained in G2 and hence it acts by conjugation, by coadjoint action on this nilpotent orbit. Okay, so I hope that these examples give you a glimpse of the non-triviality of this conjecture. And in fact, after SL3, we don't know. We don't have an explicit geometric description of the variety WG. There's a solution by Ginzburg and Kazhdan, which I will explain next, but it's not as explicit as saying this is the minimal nilpotent orbit in such algebra. Okay, any question? Okay, let me go on and explain their solution. Before I explain their solution, I need to recall a little bit about the general notion of symplectic reduction. I'm sure all of you know what symplectic reduction is, but I will take a slightly more general point of view. If you have any symplectic manifold M, and you take any co-isotropic submanifold, so a co-isotropic submanifold just means the symplectic orthogonal is contained in the tangent model of N. And well, that means that you can quotient by T and omega. And since you're quotienting by the space on which a symplectic form is 0, the symplectic form descends to a non-singular, a non-degenerate form on this vector space. So this is a bundle of symplectic vector spaces. And moreover, this defines an integrable distribution on N, which means that if you take the leaf space, tilde here is the leaf space of this integrable distribution, then if this thing happens to be smooth, it will be a symplectic manifold because its tangent spaces will be exactly the fibers of this vector bundle. So that's the general, well, it's not the most general, but it's a very general notion of symplectic reduction. And of course, as a special case, if you take a moment map for an action of a group G on M, then N is the zero-level set of the moment map. That's a co-isotropic submanifold. And the leaves here of this null foliation happens to be the G orbits, which means that the quotient of the zero-level set of the moment map by G is symplectic if it's smooth. So that's the usual symplectic reduction that we know, but Ginzburg and Kazhdan uses these, they use this more general notion. Okay, so let's review this construction. Well, actually, instead of constructing W, they construct the variety associated with N boundary components in a uniform way, and they build it from the building block Z1, which is the one with just one boundary component. So the one boundary component is the cap. So let's say we want to build WG. All these have an associated Hamiltonian action of G. So if you look at 3 copies of them, there will be 3 actions of G, and their construction is somehow a way to glue them together in a way to get something which is the surface associated with the variety associated with the pair of points. So it's some kind of gluing construction with these basic building blocks. So from the statement of the conjecture, the Z1 is G times the Slodovy slice. And it comes with a canonical map onto the GIT quotient of G star by G, which is just an affine space of dimension the rank of G. And this map is just taking the Lie algebra component and mapping it into the GIT quotient. So that's a fibration. And the key lemma is that if you take the fiber product of n copies of Z1 by this, this map here, call it N, then it's a coisotropic submanifold of the n-fold product of Z1. So Z1 is a symplectic manifold, and hence so is M. And so I've used the same notation as above here, and it's a coisotropic submanifold of the symplectic manifold M. So it's in this setup, and moreover, you can identify the leaf space. The leaves are precisely the orbits of a group scheme action. And so that's the interesting bit. And this group scheme here can be built from the universal centralizer. So that's a canonical group scheme on C associated with G, which can be viewed as the pair, the set of pairs G psi in G times S, such that G fixes psi in the quadrant action. But that's not the group scheme. The group is the kernel of this map. So it's the special property of this group scheme is that it's an abelian group scheme. And hence, if you look at the multiplication map from n copies of J to J, that since J is abelian, that's a group scheme homomorphism. And hence, you can take the kernel to get another group scheme on C. And that's the group scheme. It has natural action on N because J has a group component G here, and it acts on this component of Z1 here by right multiplications. So there's a natural action of H on N in the sense of group scheme action. So it's an action relative to C. And the key point now is that the geometric quotient of N by H exists, and it's smooth, and hence by this general reduction theory, it's a holomorphic symplectic directly. But that's not quite Zn. We have to take one step further. We have to take the GIT quotient in the sense that we take the spec of invariant polynomials. But H is a non-reductive group scheme, so it has slightly different properties than a reductive GIT quotient. And in particular, this geometric quotient exists, but it's not the same as the GIT quotient, but it sits as an open dense, as a Zariski open subset of the GIT quotient. And that's what we define to be Zn. But the holomorphic symplectic structure comes from this reduction and is only on an open dense subset of Zn. But actually, we'll see later in the talk that there's a holomorphic Poisson bracket on this space, which induces the symplectic structure on this open dense subset. So now let's zoom out a little bit. Their construction looks formally like a symplectic reduction, but we're not reducing by a group like in usual symplectic reduction. We are reducing by a group scheme H. And it's not clear what is the moment map. So can we view taking fiber product as a moment map? Can we view that as a moment map for H in particular? That's the questions I sort of asked myself when I saw this construction, and I wanted to build some general theory of symplectic reduction, which induces that as a special case. And that's what I want to explain next, that yes, there's a very nice way to view that as a reduction along a certain submanifold. Okay, so to explain this construction, I will review a little bit about groupoids. So a groupoid is a generalization of groups where multiplication is just partially defined. In fact, it's defined if and only if the source of G is equal to the target of H, where S and T are some maps from G to a space X. So as a special case, and also there's an identity map, an inverse map, which generalizes the identity inverse in a group. So of course, a group is a special case of a groupoids, where the space X here is just a point. A group scheme is just a groupoid. Where the source and the target maps are equal. So it's a fibration where the fibers are groups. But it's not a principal bundle because these groups might not be isomorphic. Also, the canonical example is the fundamental groupoid of a space X. So that's when you look at the topological space and you look at the space of path up to homotopies. And so you view a path from 2 points on this space. And of course, the source here is evaluation of this path at the starting point, and the target is evaluation at the endpoint. And then you can compose path if and only if the source of one corresponds to the target of the other. This gives us another path. So groupoids is just the axiomatization of this notion of concatenating path in a space. Okay, and there's a notion of symplectic groupoid. I won't go into the details, but it's just a Lie groupoid, where a Lie groupoid just means that G and X are manifolds and all the maps are smooth. And it has to have a symplectic form, which is compatible with the multiplication structure in some way. An interesting consequence of this definition is that there's a canonical symplectic form, which descends from canonical Poisson structure, which descends from the symplectic form of G to X. So a symplectic form, Poisson structure is sigma. And the main example of a symplectic groupoid is when you take the cotangent bundle of a Lie group. That's a symplectic groupoid where the symplectic form is just the canonical one on the cotangent bundle of the space. And the moment maps are the left and right actions. The moment maps for the source and target maps are the moment maps for the left and right actions of G. And the Poisson structure is, as expected, just a Krylov constant Suryo Poisson structure of the dual of the Lie algebra. So that's a very important example. That's the main example that we will use to get the Ginzburg and Kazhdan examples. Okay, now there's already a notion of symplectic reduction by a groupoid due to Weinstein. I will review that. Let's take any symplectic manifold M. And there's a notion of a symplectic action of a symplectic groupoid on M, which just means a groupoid action. So a groupoid action is well, in particular, it means that you have to have a map from M to the base space of the groupoid, such that the action of G on the point P is defined if and only if the source of G matches the mu of P. So that's the notion of a groupoid action. And this groupoid action has to be compatible with the symplectic forms of M and G in a certain way. The precise way in which it's compatible is not very important. Precisely means that the graph of the map is Lagrangian, but it's just a natural compatibility condition. Then Mikemi-Weinstein generalized usual symplectic reduction to this situation. And if you pick any point X in the base space of this groupoid, and then the fiber of mu at this point here, so mu is the generalization of the moment map. If you quotient it by the isotropy group, so that's the isotropy group, it's the intersection of the source and target fibers, this has a canonical symplectic form if it is smooth. So it's a generalization of symplectic reduction, which you recover as a special case where you have a moment map for a G action. Then, as we saw in the previous slides, the cotangent bundle is a symplectic groupoid, and it acts on M in an obvious way. And for all C in G star, so that's the same as X in X, then the symplectic reduction in this Mikemi-Weinstein sense at X is just the usual symplectic reduction at level C. But note here that the thing by which we take the quotient here is a group. So even though we started with a groupoid here, so that's a groupoid, in the end we quotient by a group. So it's still not general enough to get the Ginzburg and Kazhdan examples, because in their example, we quotient by this H, which is a group scheme and not a group. So it's a group scheme over C. It's a family of groups, but the groups vary. Some of them are tori, but some of them are non-reductive or additive groups. Okay. So now our goal is to generalize that, where we will replace point X here by a submanifold S of X. We will define what it means to take the symplectic reduction along this submanifold. Okay, so the setup here is that we have the symplectic groupoid acting on a symplectic manifold M, and the symplectic manifold. And for instance, we can take T star G and the moment map. Already this will give us something interesting. Now pick any submanifold S of X and let N be the preimage of S under this moment map. Also, we will assume that S is transverse to mu, so that when you take the preimage, you get a submanifold. So this assumption is that we want this to be a submanifold. Then quite generally, I mean, for any submanifold of a symplectic manifold, if you quotient the tangent space by its intersection with the symplectic complement, that gives us a symplectic vector space, for the trivial reason that when you quotient by the thing on which the symplectic form vanishes. And so the symplectic form descends to a non-degenerate form on this quotient. That's true for any submanifold of a symplectic manifold. But our goal now is to use special property of this setup here to integrate this distribution in a nice way by a subgroupoid of G. And so once you quotient by the leaves of this distribution, you get something symplectic. And there's a technical assumption here, which is that this subspace of the cotangent bundle has to have constant rank. And here, sigma, if you recall from the previous slides, is the Poisson structure of X, which can be viewed as, so a Poisson structure can be viewed either as a bivector, or if you hook any cotangent vector by the bivector, you get a vector, so you can view this as a bundle map from T star X to X. And so this is a subspace of T star X, and we ask that it has constant rank, so that it's a vector bundle. And those submanifold of a Poisson manifold, which satisfy that, are called pre-Poisson. So we'll review a little bit later why they are called pre-Poisson. It's not a very strong assumption. It's quite permissive. And the theorem is that the leaves of this distribution here, which generate, which when you quotient by its vector spaces, the leaves are the orbits of a subgroupoid of the symplectic groupoid here, G. And hence, if you quotient by GS, if you quotient the preimage of S by this subgroupoid, it has a canonical symplectic form descending from the symplectic form of M if it is smooth. And actually, this groupoid can be constructed more precisely as the subgroupoid of the groupoid G corresponding to a certain Lie subalgebraid. So we assume that this has constant rank, and so it's a vector bundle. And it happens to be a Lie subalgebraid of the Lie algebraid of G. So I didn't say that, but the Lie functor from Lie groups to Lie algebras extends to a functor from Lie groupoids to Lie algebraids. And from a Lie subalgebraid, there corresponds a Lie subgroupoid. In general, it's only immersed, but still it exists. And so that's our GS, which now acts on nu inverse of S, and then you take the quotient in the groupoid sense, and that if things are nice enough to be smooth, it will inherit a canonical symplectic form. Okay, and now let's discuss the special case where G is the cotangent bundle of a group, and mu is a moment map. So that's the Hamiltonian case. Let's take a G group acting on a symplectic manifold with moment map mu, and consider G to be the cotangent bundle of G. That's a groupoid. We define now the symplectic reduction along a submanifold S of the dual of the Lie algebra to be this groupoid symplectic reduction along S, where G is T star G. We denote it by just M, 2 slashes S, G. And note here, the important point is that although G is a group, we start with a group, the thing by which we quotient by is now no longer a subgroup. In general, it will be a subgroupoid, so it might not be a group or a cotangent bundle of a group. Okay, let's see a few of the special cases that we recover. So that's the setup, a moment map, we define this. Of course, if we take S to be just a point in the dual of the Lie algebra, as expected, you recover the usual symplectic reduction at level C. More generally, if you take a Lie subalgebra H, and you take C plus the annihilator of this Lie algebra, then you can view C as an element of the quotient, or just the dual of the Lie algebra of H. And if you take the quotient along this S, you recover the symplectic reduction of H, where H is the Lie group with Lie algebra H, at level C, interpreted as an element of the dual of the Lie algebra of H. Another interesting case that we recover is if you take a Poisson transversal. So a special case of that is a Slodový slice. So as I said in the previous slides, the Slodový slice is when you take F plus GE, where FEH is an SL2 triple. It doesn't have to be regular. And you view this as an element of the dual of the Lie algebra by means of an invariant bilinear form. So note here that I'm going back and forth between the smooth case and the complex symplectic case, because the theorem works in both cases. I mean, symplectic reduction can be stated both in the C infinity case or in the complex, in the case of complex manifolds and holomorphic symplectic forms. The idea is the same. As long as the result is smooth, it generates a canonical symplectic form. The notion of Poisson transversal just means that if X is a Poisson manifold, the restriction of the tangent bundle to S is a direct sum of TS plus sigma TS annihilator. But a nice, I mean, a very important family of examples is when we take these Slodový slices. And it's a well-known fact that if you take the preimage of a Slodový slice by your moment map, this is a holomorphic symplectic submanifold of your original symplectic manifold from M to G star. But in this case, if you take a Poisson transversal or Slodový slice, this stabilizer here is trivial. And so you recover this fact, because now the symplectic reduction around S is just the preimage of S. And so you recover this fact that the preimage of S is a symplectic submanifold of M. Another interesting example is when you take a coadjoint orbit in the dual of the Lie algebra, then you get something new. So all these previous examples, you could argue, well, those are already new. There's not nothing very much interesting about that. The only interesting new thing will be the Ginzburg and Kazhdan examples, which will be something genuinely new. But already in the case of a coadjoint orbit, you can see that this is not a symplectic reduction in the usual sense, because now the stabilizer is some kind of universal centralizer above this coadjoint orbit is the set of pairs G, C, such that G fixes C. This is not a group nor a cotangent bundle of a group. And as a special case, if you look at the cotangent bundle of G, with the right action of G, a reduction along this quadrant orbit, you get O times O, which is not something you can achieve by a standard symplectic reduction of the cotangent bundle at a level C. So I think that's something to something interesting. Okay, so now the only reason why I introduced this symplectic reduction along some manifold is that we can recover the Ginzburg-Kazhdan examples. So let me revisit their construction in this new setup. So recall that their Zn is a GRT quotient of this fiber product Z1 by this particular group scheme H, built from the universal centralizer. How do we get that? Well, consider the action of G on T star G by right translations. So it's simply the lift of the action of G on G by right multiplications. This lifts to an action of the cotangent bundle. This has a moment map where if you trivialize the cotangent bundle in this way by left translations, the moment map is simply the projection along the Lie algebra factor. Now let's take a principal Slodovy slice. Then the variety Z1, from the definition of the Moore-Tachikawa conjecture, we said that this should be G times S. And well, this can be viewed as just the preimage of S under this moment map here. And as such, so as I explained in the previous slide, this can be viewed as the reduction along S, because that's the case where the GS, the stabilizer, is trivial. So that's the special case of this construction. Now, how we get the general Zn? Just take the n-fold product of everything. So n-fold product of this G action on T star G. And then it has a moment map, which is just the n-fold product of the original moment map here. Okay, and now what is the submanifold we take? We simply take the diagonal embedding of the Slodovy slice in G star n. So that's just the set of pairs C, and G star n for all C in S. So that's pre-Poisson manifold, a complex manifold, which is pre-Poisson in this Lie algebra of this moment map here. And hence we can just consider the symplectic reduction along this submanifold. And it happens that if you take the preimage of this diagonal, that's exactly this thing in the Ginzburg-Kazhdan construction. And the stabilizer here is exactly this H here. And hence, the conclusion is that the Ginzburg-Kazhdan construction can be viewed as the symplectic reduction of T star Gn by Gn along this submanifold. Where here I added another slash here because we're taking the GIT quotient. So you can think of that as some kind of hyperkähler quotient of T star Gn by Gn along the submanifold. But in any case, the symplectic structure comes from the geometric quotient, so the usual symplectic reduction on the submanifold, which happens to be an open dense subset of this GIT quotient. That's where you get the holomorphic symplectic form from this general symplectic reduction procedure. Okay, so that's the construction that we get. Now there's another slice after that, which is about an interesting thing about the general theory of symplectic reduction along some manifold, namely a recipe to get integral systems. And then after that, I will discuss quite generally how do we get Poisson structures on these GIT symplectic reductions, which induces the symplectic structure on the open dense space. But first, let me discuss a bit about integral systems. So this is something I haven't really explored yet, but I think could be a nice avenue for research. Okay, let's take the most general setup of symplectic reduction along some manifolds. We take a symplectic groupoid acting on a symplectic manifold N with this moment map, and we take N as a pre-Poisson submanifold. Then, as a consequence of being pre-Poisson, this distribution D here where I recall sigma here is the Poisson structure on S. So that gives us an involutive distribution on S, and you can take the leaf space. And this happens to enumerate a canonical Poisson structure from X, a canonical Poisson structure from sigma. If this distribution is regular, meaning that the quotient is smooth. And once you get this notion of symplectic reduction along some manifold, it's not difficult to see that the moment map now descends to a Poisson map on the symplectic manifold to this Poisson manifold. So in other words, you can view that as a symplectic realization, so a Poisson map from a symplectic manifold to a Poisson manifold. And in particular, if sigma S happens to be 0, we obtain an integral system in a very loose sense. I mean, the dimension might not be twice the dimension of the base space, but you can play with examples so that you get this. And this is just an algebraic condition, a linear algebraic condition on the tangent spaces, which can be formulated in this way, that the intersection of tangent model of S with sigma, the image of sigma is contained in sigma, the image of sigma under the annihilator of TS. And so, for instance, if you take any Hamiltonian manifold, the moment map, any pre-Poisson submanifold S, so that's just a submanifold of the dual of the Lie algebra, satisfying this some kind of Lie theoretic condition in terms of the coadjoint action, or if you identify G with the dual of the Lie algebra, this is just a condition with the Lie bracket on G. Then this is possibly degenerate integral system. And moreover, it's a submersion at any point where mu is a submersion. And as a special case, if you apply that to the Ginzburg and Kazhdan examples, using this point of view as a symplectic reduction on some manifold, you get Poisson maps onto C, where C was defined as the GIT quotient of G star by G, which is just an affine space of dimension the rank of G. And in this case, it satisfies this condition where you get the 0 Poisson structure. So it's an integral system in this loose sense, but if you want a general integral system, in the sense that the dimension of the space is twice the dimension of the base, this happens if and only if n is 0. And in this case, n is 0 means we get the universal centralizer. That's, as I explained, that's the space associated with the sphere. And so we recover the well-known integral system on the universal centralizer J to C, which has to do with the constant total lattice. And so I think that's something which would be worth investigating if we can get some non-trivial integral system from picking a Hamiltonian manifold and some manifold of G star of the dual of the Lie algebra. For instance, even if M is T star G, and you consider right action, can we get some interesting integral systems by picking appropriate submanifold of the dual of the Lie algebra. Okay, so I have maybe 5 minutes left. So in this few minutes, I will explain ongoing work, which has to be the singular complex analytic version and the stratified symplectic version. So this is something that I've started talking with Peter recently in the last few weeks or months. So now we do everything in the set of holomorphic symplectic manifolds. So if M is holomorphic symplectic, G is a holomorphic symplectic groupoid with a moment map, and S is a complex pre-Poisson submanifold. And there's a technical assumption here, which is that we assume that this mu inverse of S is reduced as a complex analytic submanifold, subspace of M. Possibly we'll be able to remove that assumption, but for now we need to use it. But in the Ginzburg and Kazhdan example, it's not very a problem because this mu inverse of S is smooth actually, so there's no problem here. And also we'll assume that there's a complex analytic quotient here, which we'll denote by 3 slashes. So and this will be our appropriate notion of the symplectic reduction of M by G's in this, this analytic sense. And by complex analytic quotient, I just mean the complex analytic space with a GS invariant holomorphic map, such that holomorphic functions on the base space here can be obtained or isomorphic to the GS invariant holomorphic functions on the top space here, nu inverse of S. So for instance, if nu inverse of S is a complex affine variety, this ring of invariant polynomials happens to be finitely generated, then we can just take the spectrum of the ring of invariant polynomials, which will satisfy this. Then in this case, there's a canonical holomorphic Poisson bracket on this complex analytic space, which is symplectic on an open dense subset. And holomorphic Poisson bracket means at the level of the sheaf of holomorphic functions. So we have a Poisson bracket on the structure sheaf here. And this symplectic, this Poisson bracket, when you reduce it to this particular open dense subset, which is contained in the smooth locus, it comes from a genuine symplectic structure. So the Poisson bracket is obtained from the symplectic form, taking the Hamiltonian vector field associated with these functions. And so, for instance, this endows the Ginzburg and Kazhdan varieties with holomorphic Poisson structures compatible with the holomorphic symplectic structure of the geometric quotient. And finally, I will just briefly mention the future work which we just recently started working. What I thought would be interesting to mention it is the stratified version, because so that in this theorem here, we construct we have a holomorphic symplectic structure on an open dense subset, but we would like to have actually a complete stratification of this space into holomorphic symplectic manifolds, such that the symplectic structures can be obtained, all obtained from these Poisson structures. So this is already known for the case of symplectic reduction in the usual sense. So if G acts freely on a symplectic manifold with a moment map, then this is a smooth symplectic manifold. But in general, Sharma and Lerman famously showed that you get decomposition of the space into smooth symplectic manifolds, which fit together very nicely in the sense that they form a stratification of the symplectic reduction. And moreover, there's an appropriate substitute for the algebra of smooth function inside the algebra of continuous functions with a Poisson bracket, such that these space are symplectic leaves in a suitable sense. And so the question now that we're working on is, does the same hold for symplectic reduction along a submanifold, or even more generally, symplectic reduction by a groupoid along a submanifold? And we hope to have a positive answer at some point, and that's the end of my talk. Thank you.